Founded in 1928 and part of the ACS Group since the 1990s, Vías y Construcciones has become one of the top construction companies in the Spanish market. With a railway vocation, Vías y Construcciones is the leading company in railway construction work in Spain, and quite particularly in high-speed work. Of the construction of the northern-northwest high-speed corridor Valladolid-Burgos, Vías y Construcciones has completed the Quintana del Puente Estepar track installation section. The infrastructure of the line will feature an electrified UIC gauge double track and was designed to reach a maximum speed of 350 km per hour, 217 miles per hour, suitable for mixed traffic. The unique feature about the section is that only a single track will be installed instead of the habitual two. Nonetheless, the track formation was built for the standard, so the track may be doubled in the future. The work includes the construction of a ballasted high-speed line over 35 kilometers, 21.7 miles, the construction of an advanced train parking area, 2 ballast stockpiles, and the implementation of expansion joints along the 1.4 kilometers of viaducts. The track characteristics are a ballast thickness of 30 centimeters, 11.8 inches under the sleepers, a 1.1 meter, 3.6 foot ballast shoulder, a ballast shoulder slope of 3-2, lateral sub-ballast gable slope of 5%. We shall also mention the characteristics of the track materials, highlighting the use of Type A ballast, UIC 60 rails supplied on-site in 270 meters, 886 feet bars, monoblock sleepers, and SKL1 fasteners. There is an existing assembly and maintenance base in Villada, which pertains to the Valladolid-León high-speed line, which was used in the construction of this section. For the protection of the existing infrastructure, an asphalt surface treatment is carried out in order to protect it from the heavy construction lorry traffic and waterproof it. Once this is done, the topography work is carried out. Those works will consist of the geometric check of the substructure or formation layer, the preparation of the fixed settlement positions for the theodolites, and the installation of references along the line. Once the sleepers have been distributed along the stretch, the initial ballast bed, 14 centimeters, 5.5 inches thick, is formed with a lorry and a spreader. The sleepers are positioned using a special width crawler loader backhoe equipped with a hydraulic tool, and later the distribution geometry is adjusted and squared manually. The rail loading operation is done at the Villada base, with each convoy carrying 30 bars, each of them 270 meters, 885 feet in length. The unloading and laying procedure is carried out with rollers and an automatic rail laying gantry on crawlers. It involves the following activities: installation of rollers every 25 sleepers, installation of height adjustable loopholes for adequate rail unloading as the train exits, rail unloading with the automatic rail laying gantry, the release of rollers and placement of the rail in the final position on the bed plates using a rail positioner. The fasteners are secured by applying provisional torque. Thus, with roller and gantry assembly, a complete track-laying train can be unloaded in a single shift, which means daily installation performance of 4,050 meters, 2.5 miles of track. As the rail is laid, the track skeleton is assembled and squared. The sleepers are automatically squared with the automatic feed machine and then tightened and adjusted with the fasteners. Once the assembly is finalized, the ballast trains are loaded at the 2 stockpiles on site, and the ballast is distributed over the track. The so-called working train, comprised of a ballast tamper, profiler and stabilizer, does successive passes or lifts until it reaches the first level elevation, so the rail elevation geometry is in a 20 mm (0.7 inches) position with respect to the definitive position. The performance for this work has been 4,000 meters, 2.48 miles of track per shift. Once the first leveling is finished, the track is welded and the rail de-stressing is continuously done at 1,080 meters, 0.67 miles each. The welding is later verified with ultrasound auscultation. The de-stressing is achieved by loosening the fasteners on the 1,080 meter, 0.67 mile bars, and hydraulic jacks are used to create traction in the rail that is equivalent to the thermal lengthening. Immediately thereafter, all of the fastenings are tightened and the free ends are welded. Finally, the second leveling is done with tamping, profiling and track stabilization. Minimal addition ballast is needed for this. The turnouts, comprised of a switch, intermediate area and crossing, are pre-assembled at the viada base and moved along with the gantries that will be used to unload them on MMQ flat wagons. Once unloaded and situated in the definitive position, the rest of the turnout is assembled on site. With the switch positioned and linked, the ballasting, tamping, leveling, alignment and profiling is done until the first leveling is completed. Then it is stabilized. Finally, the welds are done and the turnout is neutralized. The second leveling and stabilization is done together with the entire project superstructure. After completing the work corresponding to the first leveling, the 4 expansion joints planned in the project are installed, 3 of them in one shift. The installation includes lifting the provisional track stretch and positioning the ballast walls to prevent the ballast from falling into the viaduct joint. This leaves the space for the pre-assembled expansion joint to be installed using a set of gantry. The expansion device installation is done at the same time as the general welding and release work, so they are at the correct depth after the de-stressing.